7000. Let me just change the lights a little bit. It should be better. And why do we need those? Okay. There we go. And welcome to everyone who's watching online as well. So, a couple of things. Any questions just about last week in terms of the lecture materials, reading, course profile, or practicals? Nope. Okay. If you do think of anything, just let me know as we go through today. Okay, so this week we've got a lecture. We're sort of jumping into the main part, or the key scientific underpinning of the course, and we also have a practical this week, so running on Wednesday. And so this week's practical, you'll be using the QGIS software again. You'll be working with all of the different satellite image field data sets that we're going to be interpreting in the field in week 3, and we'll also be covering in week 4 in practical 1.4. So this week's really about using QGIS to interpret or critically assess what's going on with the different image data sets. So just in terms of what we're going to cover in the lecture today, the course is broken into a number of modules, as you saw looking at the main structure. This is the first one. It's the scientific underpinning, essentially, of how we obtain images and then how we actually start to pull quantitative information out of those images. So we are going to talk about electromagnetic radiation and why understanding some really simple applied aspects of physics and how light and energy interact with features is going to help us interpret airborne and satellite image data sets. So we are going to talk a little bit about the sun today. There's just an image from the NASA's solar observatory there. So we commonly see the sun as a white ball. It's a little bit different to that. But we're not necessarily going to be looking at the sun. We're going to be looking at the energy that comes out from the sun and how it interacts with what's in the atmosphere, what's on the land surface and water bodies. So the second graph is one you're going to see a lot of during today and subsequent weeks. And what it shows along the x-axis are different types or wavelengths of light. And we'll explain how we separate light by wavelengths in today's lecture. And the y-axis is the amount of energy. So this first curve is showing you how much energy is coming out of the sun, and it's got a maximum amount of energy coming out in this sort of 0.4 to 0.7 micrometers, which is times 10 to the minus 6 meters, a thousandth of a millimeter wide. That's where most of the sun's energy comes from. Interestingly, that's where our eyes work really well for those colours, and pretty much anything that uses sunlight has built physical and chemical properties that use that energy. This other curve down the bottom is the amount of energy coming from the surface of the Earth. The Earth's a lot cooler, so it emits energy at a much longer wavelength down there. And what we're going to talk about is how the energy from the sun hits stuff in the atmosphere, vegetation, soil, water. Some of it's absorbed, some of it's reflected. And because different features like gases, solids, liquids have different physical structures and chemical compositions, they absorb and reflect light in unique ways. They have a signature almost. So this graph on the right, you're going to see all through the semester, and it's a spectral signature graph for 3 different types of eucalyptus leaves in different colours there. So the x-axis is the types of light wavelengths, going from blue, green, red, and near infrared. And the y-axis is how much sunlight's been reflected. If the target was reflecting all the light, there'd be a line straight across the top. But these are 3 healthy leaves. They're absorbing most of the visible wavelengths of light, which is that part of the spectrum. and using it for photosynthesis. They're reflecting a lot of the near-infrared light and also reflecting some of the shortwave infrared. There's very distinct absorption features here and here and here due to water content, and then all of these other chemicals are absorbing light in certain wavelengths. So things like starch, proteins, sugars, cellulose, which is another pigment, they're all controlling how much light's absorbed. So those signatures, we're actually going to go out and measure these in the field for different types of surfaces. That's also what you get out of every single pixel in an image. So if we're going to interpret an image or process it, we need to understand spectral signatures and how they're produced, which is what today is about, essentially. Okay, so why are we getting into the science part of this? There's two levels. Some of you are going to be in positions where you're collecting satellite and airborne imagery and have to turn it into usable maps and information. So the skills and knowledge that you use to collect a satellite image, process it, and deliver, information that people can use depends on understanding these electromagnetic interactions. Some of you are also going to be in positions where you're not going to be doing the mapping, but you might be looking at, output papers, reports, other information where someone's done a study or they've measured something using satellite imagery, and you have to critically assess and determine whether that information's correct and usable for whatever job that you're in. So even though you're not doing the mapping, you've got to figure out whether it's going to work or not. So understanding how images are produced, the role of electromagnetic radiation in them is really critical, because if you understand those interactions, it helps you go from, okay, that's a nice sort of image or picture of Australia, to if we go into each pixel and look at its spectral signature, what does it tell us about the mineral composition of the soils? What does it tell us about, how much biomass is there, for the crops? Will it let us separate sugar cane, from cotton? If we're just looking at sugar cane, will it let us estimate, the likely sugar content of the cane? So doing all of those things depends on having this basic scientific understanding. Yeah, so as an example, to produce that map of biomass, it wasn't someone just downloading a Landsat image and pushing a button. It was, okay, how do we actually get the right wavelengths of light? How do we link that up to field measurements? How do we build algorithms that work in, really dense tropical forests like the wet tropics in North Queensland, the 60, 70 metre tall forests in Tasmania, through to areas of grassland and shrubland in the desert? And those models are built on understanding how electromagnetic radiation interacts with vegetation, setting up the model to run in each pixel, and then producing a map like that. And we'll come back to this example throughout the semester so you can see how it was actually built. So today is the core module. So as I said, it's at the start of the course. It'll help you understand images and how to do all of the processing. Once we get through this week and next week, then we'll get into looking at the different platforms, so satellites and aircraft, all of those things, and the different data sets they collect. Then we'll get into image processing or information extraction approaches. And then the final, actually 3 sections is about project design. How do you take all of these approaches and actually set up a project where you're given a problem and you can critically assess that problem to go, okay, based on that problem, we need these image data sets. We'll go through this processing and it'll produce this product, and this is how accurate it is, and we can show that it meets, the needs of whatever problem you're trying to solve. And we will talk about information and communication. Hopefully one of the main things that you learn through, being at university, whatever your courses are that you're doing, is communication in terms of the areas that you work in, how to do that effectively, but also that basic problem solving and project setup and operation as well. Those are critical skills for any activity outside of university. Okay, so outline for today. 6 areas. I'm going to finish talking about the field practical, which Chris Rolfson is going to explain a bit more in this week's practical. Every section's heading is in red. This is a foundation presentation for the rest of the semester. So talk about electromagnetic radiation a bit more. Get into spectral reflectance signatures. Remember, this is the information in each pixel, so it's really how you interpret a pixel. Going to talk about some essentially basic physics under radiation principles and properties. Talk about electromagnetic radiation interactions. That'll help us interpret signatures. Very briefly touch on radiation transfer theory and why it's important, and then lead into the field exercises as well. Okay, the readings for this week. So 2 sections out of one of the online texts. So the scientific foundations of how remote sensing works. Please read through that. And then also the section on electromagnetic radiation. So both of those are designed to be highly complementary to what I present. They'll fill in the gaps in between and give you more examples, both in Australia and overseas in that context. So if you haven't already, please download the text and have a look at it. Okay, back to this image. Some questions. Some of you have done, I think, basic environmental physics before, so if you have, maybe you know the answers to the questions. If not, okay. So the first one, open to everyone, and I guess also people online, is, why is the sky blue? I mean, we can just see the edge of it in the picture. What are the main reasons the sky is blue? The starting reason is there's sunlight going through it. So then what happens? Why is it blue? Any wild guesses, or actually educated guesses, or anything? Yeah? Yeah, so it's scattering blue wavelengths of light. So what's scattering the blue light? Someone else, though. So what's scattering the blue light? Cloud, smoke, what? Yeah, so the gas molecules in the atmosphere, they happen to be physically the right size, the right physical arrangement, that their molecular structure interacts with the blue part of sunlight, and it'll scatter that as well. Same thing if you've got really clear water bodies that don't have organic matter within them or suspended matter, it's going to scatter blue light as well. Okay. Why is the river water brown? Yeah, so suspended sediment that's in suspension. So generally, so inorganic material which is floating around. Okay, so generally not organic material. Rivers can be silty and sediment laden naturally. This part of the Brisbane River is naturally silty because of our tidal range and its reach up the river, and that it resuspends the fine sediment all the time. Doesn't necessarily mean the river's dirty, in a chemical sense at this point. You go upstream to places like the Bremer River and others, that's a different story. It is silty, but it also has a lot of pollutants in it as well. So you've got, in this case, it's generally the slightly longer wavelengths, the red wavelengths being scattered by sediment particles. They're the right size for the sunlight to hit them and for the red light to be scattered around. Okay, why is the vegetation green? We've got lots of nice green mowed parks there in East Brisbane. Look over at New Farm Park, Botanic Gardens as well. Cool. Yeah, so someone in the comments has gone, okay, the green wavelengths are reflected. okay, why are the green wavelengths actually reflected? Like, why aren't the blue and red wavelengths reflected? What's going on? Yep. Yeah, so what's the chlorophyll doing? Oh, sorry, first of all, where is the chlorophyll? What's it doing? Yeah, in the leaves. Yep. Yeah, exactly. So the red and blue light is what the plants use to drive their photosystem. So it takes that from the sunlight. It doesn't use as much green light, so it reflects it. So they look green to us. But all of the plants, you've got. I mean, if you look at that aerial image of Brisbane, we've got mangroves along the creek here. We've got a whole range of the jacaranda trees through New Farm Park. Whole range of different trees in the Botanic Gardens. They've got different structured leaves, canopies, different chemical composition, different physical form. So they're all green, but sort of different shades of green. So all of those colours that we see, in the sky, in the water, and in the vegetation, those are all, we've talked about physical chemical interactions. Those are all electromagnetic radiation transfer interactions. That's just another fancy way of saying light interactions, all right? So that's what we see with our eyes. So when we're going to do it from the satellite systems, we're going to start looking at individual pixels to actually do it. So, okay, any object that's got a temperature greater than absolute zero or minus 273 degrees Celsius emits energy as well. So there's actually an aerial oblique view up in Gladstone looking into the harbour in there. So downtown Gladstone is in here, and then you've got the power plant out here, and there's another facility there. So just remember that there. So, when we look at that, we're seeing that's a record of electromagnetic radiation interactions. The sunlight's hitting the surface. There's all different features in that are absorbing and scattering light, and because of that, we can see them as different objects, and then we use other information to identify what they are. Now, we do the same thing and move to a satellite image. So that photo we were looking at before, where were we? Was taken looking into that area in there. So instead of being just a couple of 100 metres above the ground, we're now 800 kilometres looking down. Same principle applies. All the colours are due to light being absorbed and scattered or reflected depending on the type of features that are in the surface. So like a coastal estuary in here, built up artificial surfaces, coal stockpiles in here, bauxite tailing ponds from the alumina refinery here, so that's all a red colour. Different types of native vegetation through there. So that's reflected sunlight. So that's sunlight hitting the surface and coming back, whereas on the right, this is emitted electromagnetic energy. So it's not sunlight hitting the surface coming back up, it's because the Earth's a certain temperature and it's emitting energy, electromagnetic energy as well. So the water bodies are the coolest, and then as you go to different land cover types, it gradually heats up, except for where you happen to have basically heated water coming out of the power plant there and going out into the bay. So when you look at images, it's a picture, but then you start applying radiation transfer considerations, looking at each pixel in terms of what type of light's being absorbed and scattered, and then you can start to look at other information. So there's basically that particular slide there. I'm just going to jump into that, quickly, just to show a video. I hope this is going to work online as well. Let's see. Well, I'm going to break everything. All right. This is on the NASA science page. It's worth having a look at. It's an overview of aspects of the electromagnetic spectrum, but it also goes through and does explain electromagnetic energy and how it interacts with features and how it relates to satellite and airborne remote sensing. We'll come back to atmospheric windows and other things later on. So I don't know if let's see if this is going to work.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
Okay, so quick overview there. Now sort of diving into the critical part that we're going to deal with in the class here and link things through. Just a reminder to people who are on the chat online is that we're recording all of your chat as well, so if you can keep the chat just to questions, that would be helpful. All right. And that includes, just so everybody does know, and for everyone who's on Prax later on, private chats are also recorded, so I'll see everything that's written in the chats later on. So just keep stuff out, please. Okay, the key thing about electromagnetic radiation interactions, as we saw there before, and is that they let us collect images, but then use those images to look at the biophysical properties of the environment, which are controlling how much light is absorbed and scattered. So it's essentially how we start to take remotely sensed data sets and turn them into measurements. There's two levels that we can look at how, I guess, electromagnetic energy is absorbed or scattered and reflected, and also transmitted. We can start to look at the physical level, and that's what we just talked about in terms of looking at things like vegetation. That was very much dealing with leaf properties and the chemicals that are present within the leaves. But then when we started talking about the photosystems in the leaves, the chlorophyll that's present, the chlorophyll chemical acts to essentially, capture sort of the photons of blue and red light and use that in a photochemical reaction, and that's an interaction at the atomic level. So when we talk about absorption and scattering, there's a range of properties we can talk about in the environment that let us do that. And radiation transfer theory or radiation transfer equations lets us actually quantify the effect of physical structures and then also the concentration of various other molecular elements and how they relate to absorption and scattering of light. So in the water bodies that we're looking at, the concentration of suspended sediment, directly controls how much red light or, the number of red photons which are scattered. So when we develop equations that convert pixel reflectance or absorption to biophysical parameters, we use this radiation transfer theory information. So we've got three different environments there. When we look at those environments, or we take images, whether it's of atmospheric features and processes, land surface in terms of soil and vegetation, and water bodies, the colours that we see and then the spectral signatures that we see in images are the result of three interactions of sunlight. Scattering, which is also reflection, same sort of a thing. Absorption, so like in photosynthesis, the lights, the blue and red wavelengths are absorbed in a photochemical reaction. And transmission, like through a gaseous medium like the atmosphere, with light coming down to the surface, or through clear water bodies with light going through. So there's three types of interactions, and those interactions are controlled by the things I've talked around for the last 10 minutes, which is physical properties, so like the size and shape and structure of features like trees and things like that. It can also be the physical properties of soils, so in terms of the grain size distribution, the shape, all of those sorts of things. Chemical properties, so what type of chemicals are actually present, biological characteristics or processes that are going on. So that controls how much absorption, scattering and transmission occurs in the environment. But then what we actually see in a satellite image or an airborne image depends on the sensor that we're using. Like if it's just our cells, our eyes, as we talked about last week, are trichromate. They see blue, green and red wavelengths. We can't see ultraviolet light. We don't see usually into thermal. We can't see, radar or microwaves or gamma waves, okay? So we're limited to what we can see. I mean, we can build instruments that are sensitive from ultraviolet to infrared. We can build instruments that are sensitive to thermal energy, microwave sensitive instruments, all those sorts of things. So when you look at an image, what you actually see is a result of these two features. So it's essentially what's in the environment, but it's also the type of sensor that you're working with. So when you're interpreting and analysing images, that's why you've got to look at both of those things together. So let's go from global scales down to actually molecular scales. And what I do want to show you is that the colours or spectral signatures that we can see at the global scale there are actually controlled by what's going on in terms of physical structures, but mainly at a molecular level, whether it's the vegetation that we can see, whether it's the soil, whether it's the ice and snow. The clouds and the oceans, unfortunately, have been taken out in this global mosaic, and they've used a not great map projection, which anyway. But, the colours that we see there at a molecular level. So let's start to dive down into the area. So there's actually a mosaic from Planet Labs, and I think that was the January 2021 mosaic of this. So that's what the surface of our Earth looked like in January 2021, taking out the oceans. That's actual snow cover, actual vegetation cover, actual ground cover from those little shoebox size satellites. But again, let's keep zooming down so we can see what's happening. So we get to Australia, we can really see the different effects of different vegetation communities and types of underlying soils and geology. On the coastal fringes, you've got dense vegetation. You go to woodlands and savanna areas, grasslands, and then into sort of the arid interior and the northwest. Keep going into southeast Queensland now, and you can see sort of remnant patches of forest. We've got Brisbane here, Brisbane Forest Park, going out west towards the Great Dividing Range, and then essentially out to areas which are cropped, and then beyond gets more and more sparse. Zoomed in view a little bit, so we're sitting here at UQ. You can see the urban areas. You've got sort of coastal forest on Moreton and North Stradbroke Island. There's a Brisbane Forest Park. We've got these water storage features, so Wivenhoe and Somerset Dams, going out towards the main range, scenic rim down here, and then out towards Toowoomba and large areas of broadacre cropping as well. Zoom in again, it's getting closer. We can see all the individual houses and trees. UQ campus. So, all right, we're sitting down in here at the moment, individual trees. Let's go into the rainforest garden. There's an older picture, no bus stop in there. And individual leaves. If we look at a cross-section of a leaf, so we've got the sunlight coming in at the top. There's sort of an outer layer, there's this palisade layer, and then this spongy layer. That top layer here is where you've got the process of photosynthesis occurring. So you've got sunlight coming in and driving that reaction. See, the near-infrared light actually passes through the top of the leaf. It hits these mesophyll cells in here and scatters around and gets scattered out. If we zoom in even more and have a look at that top layer, we've got the top of the leaf in there. We've got a stomata or an opening. So we've got sunlight coming into the leaf, and then it's into these little cells which are called chloroplasts. That cell's got the chlorophyll chemical within it. Okay, so it's got the chlorophyll chemical and sunlight going into it. Through the stomata, you've got air coming in, which is carbon dioxide, and the plant's also providing moisture as well. So in that chloroplast, you've got a photochemical reaction. You've got sunlight plus the carbon dioxide that's come in, that essentially the plant's breathed in. You add water and light. That arrow represents photosynthesis. So it produces basically some sugar or energy for the plant, clean oxygen, which gets respired, and then water. So that process there, that chemical reaction, is essentially why leaves are green, healthy leaves. And it happens at that molecular level. So if you go back up, all the way, particularly looking at the vegetation there, those colours that you're seeing, which are slightly different, basically all a result of that process of sunlight being absorbed and used at a molecular level, and the green coming back up. We could apply the same process and look at soils, where we would look at the type of light that's being absorbed and scattered, depending on the mineralogy of the soil and its moisture content and its organic matter content. If you look at snow and ice as well, essentially it depends on the actual ice content, the volume of snow that's there as well, and how it's interacting with the sunlight as well. So we've got all of that. Let's go to a bit more detail. Let's look at satellite images and how we actually take that through to spectral signatures. So there's a commercial mango tree. Doesn't look like the nice big trees in your backyard, because someone's got to come in and pick all of those, and you're not going to do that off a 20, 30 metre tall tree. This is what mango trees look like at a commercial plantation. This is just outside Bundaberg. We were working with all the farm groups out here. If we look at that and zoom in on the mangoes, and we use a digital camera for doing that, and we zoom into each pixel, as we saw last week, our digital image is composed of layers or bands, and in this case it's a true colour image, and it's a blue, green and a red. Each pixel's got blue, green and a red. It's displayed here, and we can see it basically as being green as the plant or red there. So those in each pixel, the blue, the green and the red value, that's our spectral signature that we're going to start working with. Let's have a look at an avocado field instead. Characteristic spectral signatures for avocado plants, depending on the amount of photosynthesis going on. What we can actually do is use that information to estimate how much biomass or how tall the trees are as well, and that's based on linking it to some ground-based measurements as well. And then also use it to try and estimate how many avocados, or what's the avocado yield there. Again, it's based on looking at the spectral signature within a pixel. So when we look at images like this is a Sentinel-2 image of Brisbane, and we zoom in on a pixel, each pixel is 10 by 10 metres, and it's got a number of spectral bands in it. The spectral signature is a result of those electromagnetic energy interactions. And so just to explain spectral signatures in detail, this is a really key sequence of slides here. So it's a detailed explanation of reflectance signatures. So the x-axis are the different wavelengths or types of light. So the shorter the wavelengths, remember that's basically higher energy, sort of less distance between the wave crests, higher frequency. So we've got ultraviolet down around 200-300. This is nanometers, so it's times 10 to the minus 9th meters. Then we've got blue wavelengths, green and red, so that's visible wavelengths. And then we get into the non-visible part of the spectrum. And this is primarily reflected infrared light. So, and typically, we would refer to them as colours. They're also referred to as spectral bands. And remember, the spectral bands are the layers within the image. And a nanometer is 10 to the minus 9th meters. It's the amount of sunlight reflected into a pixel. If we had an object that reflected light uniformly in all directions, its signature would look like that. That's pretty rare to have anything that looks like that. But back to the signatures of those 3 eucalyptus leaves, what you can see is pretty much all of the visible light in the blue, green and red is being absorbed and used in photosynthesis. Only some of the green's being reflected. but lots of the near infrared's being reflected. But we can't see that. If we could see near infrared, vegetation, leaves would look really bright to us, but we don't. Okay. What you can see in the top right corner there is the instrument that we're going to be using in the field exercise. It's a handheld spectrometer. So we have several of these, and what you're going to be doing, as the student's doing in the picture, is pointing that at a target and essentially taking a measurement like this for each target. So you'll get, basically eucalyptus leaves, grass leaves, bare soil, water bodies. So you'll be collecting spectral signatures and you know exactly what it is, and it'll be highly detailed information, which you'll then analyse in the practical. So it's like a higher resolution version of what the satellite actually sees. All right. What we're going to look at in the practical data, and I might do this towards the end of the lecture, is jump into QGIS. And actually, let's see if we can do it now. Just going to stop sharing the screen, and I'm going to share it again. All right. So there's a Sentinel-2 image of the St Lucia campus, the one that you're going to be working with. If we turn that off, so just so we get context again, I am going to move over to where, so the field exercise is going to be in this field in the northwest corner of the university campus and the area around it. So you can see, well, the aerial image, you've got 10 centimetre or so pixels, whereas Sentinel you've got 10 metre pixels, and this is a false colour image, so I've got the near infrared band displayed as the red colour. As you saw last week, we can go into, click on the information button, go to a pixel, and in essentially the information button box there, you'll be able to see the actual spectral signature values. So that just gives you a list of the values. If I expand that out, which isn't particularly interesting. What is interesting is if we look at a graph. So so we've got 4 bands. We've got a blue, green, red, and near infrared. Okay, and so that's for the grass in the middle of the field there. The unfortunate thing with QGIS is it doesn't keep the y-axis stable. So if I look at river water, you can see it's got a very different signature in the blue, green, red, and near infrared. Likewise, if I look at let's have a look at the roof of the Forgan Smith building here. Again, another really different signature. So in today's practical, you're going to go through this, looking at the different data sets and then how we're actually going to link that to the field. In the field, we're actually going to go out and measure these on the ground in this area out here as well. So I'll just stop sharing that and go back here. Okay. All right, there's a more detailed example. So the different coloured lines are going to be different spectral signatures of different targets. The x-axis is the same as what we were looking at before. It's showing you different wavelengths of light, but this time instead of being nanometers times 10 to the minus 9th meters, it's actually in micrometers times 10 to the minus 6 meters. These units will change around all the time, but where the regions sit is the same. So we've got blue, green, red, and near infrared. So our Sentinel image, it's only got basically one band in here, another one in green, another one in red, and then another one in near infrared. This is a more detailed spectral signature. So if you look at the blue is the water body, it's reflecting visible light. The green is vegetation, so you can see it's absorbing most of the visible, and it's got a peak in the green, but really reflecting lots of near infrared. The concrete is almost reflecting uniformly across all wavelengths. And then sand is quite bright, particularly in the green, in red and near infrared. And then snow, which we're not going to see a lot of, super high in the visible, and then it drops right down. So now this is the fundamental basis of using satellite imagery in terms of distinguishing individual cover types or features. You can see these are all different land cover types. They've got different signatures. But we can also look at certain regions, like that red region of the spectrum, and measure how much light's being absorbed and use it to estimate the amount of chlorophyll that's in the plants or the amount of photosynthesis. Or we can look at the near-infrared region, and basically the more plant leaves you have or the more biomass, the higher that actually is. So near-infrared's a critical part, of estimating plant properties. Okay, a couple of radiation principles and properties before we have a break. So the first three are quite important. The first three actually relate to what was covered in that NASA introductory video before, and I'm just going to go into them. The final three, in terms of Stefan Boltzmann and Wien's law, are there for information. It's not something you've got to memorise. You just need to know, what the main points are that they represent. Okay, so why are these principles and properties critical? As I keep saying, if you understand how light interacts with features in the environment, you can use it to interpret images. And that's why you'll often find that, people who are atmospheric scientists have a high-level understanding of how, let's say, if they're interested in gases in the atmosphere, whether it's methane, carbon dioxide, or other gases, they have a really good understanding of how those gases interact with sunlight, and they use that knowledge to collect satellite imagery and estimate concentrations of those gases. Likewise, people who look at water quality in lakes, rivers, streams, basically drinking water dams, they also understand how light interacts with water bodies, particularly organic matter, inorganic matter, chemicals and algal blooms, and they use that knowledge to collect satellite images and process it. So the key point there is you'll see a lot of people using remote sensing who won't identify as, I'm a remote sensing scientist or an Earth observation scientist. It's like, I work on this environment, this problem, or I look at, forecasting wheat yields, and they have super detailed understanding of each environment, and they use that to collect and process imagery. So it's quite fundamental. So understanding these interactions lets you do the processing and that, but it also lets you select the best data set. When you see Chris Rolfsamer talk later on, he'll talk about coral reef and seagrass mapping. Actually, today's International Seagrass Day. So if you wanted to map seagrass under the water, and you're like, great, it's nice, dense, thick vegetation, we could get blue, green, red, near-infrared, multispectral data, excellent. The problem is that water absorbs near-infrared. So if you tried to look at a near-infrared image of a water body and it's the seagrass underneath it, you're not going to see anything. So understanding how your target or environment interacts with energy helps you select the right data sets. And then it leads you to the processes that you use to identify features in images and then measure biophysical properties of interest. Okay, so wave and particle theories to begin with. So this is essentially letting us make the link between how do you relate the physical structures of features which are in an imaged area, whether it's in the atmosphere, on the ground or in the water, to what we actually measure in a pixel. So there's the physical structure of them. There's also what it's actually made up of in terms of composition and chemistry. So on one hand, we can use wave theory to explain how physical light, sunlight, interacts with features in the environment. The blue sky example is a good one there, where we can use wave theory to explain, well, why does the sky actually appear blue if it's sort of clear and there's not many pollutants? Well, you've got sunlight coming in with its blue, green and red light, or basically photons, all that energy combined together. And essentially the molecules that make up our atmosphere, which is mainly oxygen, nitrogen, and some others, those molecules are the right size that the light, which has blue wavelengths, which is typically around 400 nanometers between the two crests, or 0.4 micrometers. The blue wavelengths of light are the right size that they interact with the physical structure of those air molecules and get scattered. The green and red, essentially light, the photons, don't interact with those molecules as much, and they pass through the atmosphere, okay? But your blue wavelengths, or the blue wavelengths of light, get scattered. So that's using wave theory to explain that interaction. So at the atomic level, that's when we get to start talking about particle theory, and we start talking more about something I mentioned before, which is photons, which are packets of energy, which are, essentially, they're sort of the most basic sort of unit, if you want, of energy that's being emitted from anything that's above absolute zero. So the sun's obviously emitting billions of photons, and depending on the temperature of the object that's emitting energy, it's going to emit different photons with different levels of light. What this graph shows you is we've got wavelengths, so micrometers, 10 to the minus 6 meters. Here's the visible part of the spectrum, sort of 0.4 up to 0.7 micrometers. This is ultraviolet, and then this is into infrared. The different curves refer to bodies with different temperatures. So it's in degrees, it's in Kelvin here. So the Earth's temperature is around 273 Kelvin on average. That's roughly the Earth's emission curve. So the bulk of photons coming out of the Earth have a peak around sort of 10 micrometers. Where if we look at the sun at 6,000 Kelvin, that top curve is showing the energy distribution from the sun. The majority of the photons being emitted from the sun basically they're the blue, green and red photons in that level there. All right, so the spectrum we talked about before that was shown in the video. Question?
With Earth's emission spectra, are any satellites optimized for looking at that?
For emission spectra? Yeah. So longer wavelengths? Yeah. So there's actually, once you get into microwave sensors, there's a whole area of passive microwave sensors. And when you look at those, some of those are used to look at temperature, some of them are used to look at a range of different, physical features on the Earth's surface. They tend to have really large pixels, like 1 kilometre to 10 kilometre pixels, to pick up enough energy. There's also a lot of that done rather than looking at the Earth, looking outwards as well. That's something we're going to have, when we get into sensors, we're going to have a week looking at passive sensors, and that'll be included within that. But we'll also look at active sensors in microwave as well. Yeah, it's really, really low. That's why really large pixel size to pick up enough energy off the surface. Good question. All right, electromagnetic spectrum. Not going to dwell on it too much. Basically, essentially, really high frequency, short wavelengths, high energy, sort of down this end of the spectrum. Here's where our eyes work. This is giving you an idea. So this is nanometers, 10 to the minus 9th meters, micrometers, sort of bacteria, virus cell, but then getting into meters, and then radio waves, longer, etc. And then just some other dimensions there to have a look through. The bulk of what we're going to talk about in the course is going to be in the visible, infrared, and then microwave portion of the spectrum that we're going to deal with. So yeah, we're generally concerned with our eyes working in that area and sensors which work generally to, you're right, so infrared, microwave sensors as well. Measurement units. Okay, so you could measure, well, if you've got a light meter, that essentially gives you a measurement of the strength of light sort of hitting your particular sensor. All right. If you want to, like if I held an instrument up towards the light or the sun, at the most basic level, you've got an instrument which is trying to catch photons or energy coming towards you and then count them, right? The most basic unit would be how many photons are actually, hitting your particular sensor, okay? But we need to standardise that a little bit more. And there's some basic physical measurement units which are there. We won't use these a lot this semester. They'll probably come up a lot more next semester. We introduce them now because when you do read across different application areas, you'll hear people talk about different measurement units. So if we go up from sort of just counting individual photons, if the first measurement term there is radiant energy, so joules. So it's really how many photons are you counting. If you do that per unit time, like per second, how many joules per second, it's like how many photons are you counting per second. So it's energy per unit time. So if I measured, for a second, I'd get a measurement in sort of joules there. And then you've got a density measurement which is incorporating per unit area. So a watt is sort of that radiant flux, which is a joule per second. If we measure the amount of energy but have a certain size detector, we can work out how much energy is arriving sort of per unit area. If we make that measurement for a specific viewing angle, a three-dimensional angle, if you think of a cone, that's like a three-dimensional angle. So that three-dimensional angle, you can't measure it really in degrees. So we actually have another term called a steradian, which is it's essentially a three-dimensional version of degrees. And then if you measure it per unit time, per unit area, per angle, per wavelength unit, it's spectral radians. We introduce those here so you understand what they are, but we're not going to use them a lot, particularly because things get confusing with steradians. And there's some more explanations of steradians in the notes if you want to look at them. All right, finishing off with just the two laws there. So the Stefan-Boltzmann law provides a basis for distinguishing objects based on measurements of emitted energy. The key takeaway for, I guess, this class is the temperature of an object controls the amount of energy which is emitted from an object. We saw that with the curves showing energy coming out from the sun and the earth before. So when we look at this equation here, it's going to show the term M, which is the amount of energy coming out, being a function of T, temperature. So this equation is Stefan-Boltzmann law. So M is the amount of energy coming from an object. It's essentially its emissivity times a constant by temperature to the fourth power. Essentially just looking at that equation, temperatures to the fourth power, so very small changes in temperature produce very large changes in the amount of energy. So again, the key point here is temperature controls the amount of energy coming out of an object, and it's very sensitive to that. All right. Okay, Wien's displacement law. Okay. So the wavelength of maximum energy emitted depends on an object's temperature. That gets back to one of the graphs I showed you before where The sun, because of its specific temperature, tends to have a maximum wavelength at which it emits energy at around 500 nanometers or 0.5 micrometers, which is in the blue-green part of the spectrum. That's where the majority of energy is coming out of the sun. Whereas the Earth, which is much lower temperature, it tends to have the wavelength at which most of that energy is coming out is around 10 micrometers, which is essentially thermal energy that we can feel but not actually see. So if you wanted to work out at what wavelength you were sort of emitting energy, you essentially take a constant, which is that, and then divide it by your actual temperature in Kelvin, and it'll work that out. So if you took the temperature of the sun, which was around 6,000 K, and put that in the denominator, and then on the top you put 2898, 2898 divided by 6,000 is about 0.48. So 0.48 micrometers, that's where most of the energy is coming from the sun. So it's just showing you there's some solid relationships there. There's some additional supporting slides that go in and explain the relationship between wavelengths and energy in photons, as well as frequency and energy in photons as well. Last one, conservation of energy. When you look at an image like that, and this is part of the interpretation I was trying to make before, is it's an area that's been illuminated by sunlight, so blue, green and red light together, white light. So you've got essentially 100 units of sunlight hitting that, and it's being differentially absorbed and scattered. But essentially all of the photons coming in and hitting the surface, they've either got to be basically absorbed, scattered and reflected, or transmitted. So there's no sort of net loss or net gain in the system there. So that's a fundamental sort of rule for interpreting image analysis, in that where have we got that when you look at the signatures that you see there, there's incident energy, and it's broken down into what's reflected or scattered, what's transmitted or absorbed in that area there. All right, I'm going to stop there and also just pause the recording on the Zoom. And basically, if we have a break now, probably for the next, we're at 5:03. So if we're back in here and starting at 5:10, so 7-8 minutes from now, we'll finish off with interactions and then get into introduction to some of the field work. Okay, we might get going again. So just a couple of things. Any general catch-up questions just on what we covered in the first part? I know some people have probably covered a lot of this in physics before, and it was super simple, an overview, whereas other people haven't come across this before, and it's quite different to what you've looked at as well. So we are going to have to sort of let things meet in the middle a bit there. All right. And I think we've now got everyone online back again as well. If people do have issues with any of the audio and video, type it into the chat and we can try and address it. We'll also make sure that there's some of the updates included in the slides which are loaded as well. Okay, so first part, of the lecture today was some of the basics in terms of electromagnetic radiation. What is it? Why is it critical for remote sensing? Well, primarily it's the information which is in each pixel as a spectral signature. All right, so what we're going to do now is have a look at spectral signatures, the information in each pixel. What is it? Bit of an overview of what controls it in different environments and what makes it a little bit complicated as well. And we'll finish that off, and then I'm going to do a little bit of geospatial data essentials, so we're all on the same page for this week's practical and the field practical next week, which I'll talk about briefly as well. So I'm briefly going to talk about measuring or measurement units in 4.1 and 4.2. Critical part of this section is 4.3 about spectral reflectance curves or signatures. Okay, so spectral radiance. Typically any term where you see the word spectral in front of it, what we're trying to convey is that in this case it's radiance, but it's measured across a range of different portions of the electromagnetic spectrum. So spectral radiance is essentially measuring, blue, green, red, near infrared, shortwave infrared radiance. It's how much light is coming into a sensor per unit time, per unit area, per wavelength of light. So all of those sort of qualifications, as in it's the amount of light coming in, like even if it's to the camera aperture in your phone, that's actually measuring spectral radiance, in that the camera in there has a set field of view. Okay, so it's looking out, so it's capturing photons which are going into it. It's taking that measurement over basically a set view angle. It's taking the measurement over a set amount of time when it turns it on. It's got a set imaging area, and it's measuring in a certain wavelength. So that physical quantity that's measured, out of whatever the light meter that comes off your sort of, CCD array or whatever in there, it's spectral radiance is the term there. Spectral radiance we don't deal with a lot though with image data sets. We tend to work with reflectance. Reflectance is a ratio measurement. It's essentially if, as an example, we've got a light coming down here as the source, it's hitting the table, and there's light coming back up. That's reflected light. As a measurement quantity, there's a certain number of photons coming down from the light hitting the table. That's the irradiance, if you want. So from that light coming down, it's illuminating the target. Now, not all of it is reflected away. Some of it's absorbed, but because the lino on the table is different to the plastic on the computer, on the monitor top, the amount of reflected light is different. So it's much lower here. Light's being absorbed, whereas most of it's actually being reflected off the table here. So if we had a perfect reflecting object, the radiance would be almost the same as irradiance, and that term would be 1. Maybe it's about 0.7 or 0.8 for the table here, and whereas for this it might only be 0.3. So reflectance is a relative term. When we look at satellite images, the irradiance term is typically how much sunlight's hitting the surface, and then radiance is how much light's going back up to the sensor. So rather than looking at a light and a bench top, let's look at a tree. So the yellow beam is incoming sunlight or incident energy. So that yellow beam there is the equivalent to the irradiance term. So it's light coming in, hitting the surface of the tree. Now, depending on the structure of the canopy, the structure of the leaves, and the chemicals which are in it, we've got a whole range of different I guess, photochemical and photostructural interactions actually going on, and some of the energy is scattered or reflected, and some of it is going to be transmitted through the leaves, and some of it's going to be absorbed. So that part of the diagram is actually showing you that conservation of energy principle. You've got all that yellow light or the sunlight coming in, and it's partitioned into those three interactions. Some of it's going to be scattered or reflected, some of it's going to be transmitted, and some of it's going to be absorbed. And typically what we measure in our eyes, if we're looking, or if it's an airborne image or a satellite, this is what the satellite actually measures. And the reflectance, so radiance divided by irradiance. So there's your irradiance term, and then there's the radiance. So the satellite measures that bit, and you've got to estimate how much light's coming to the surface there. All right, so we'll come back to that in a minute. Okay, there's different sorts of reflectance. There's useful and not useful reflectance or scattering as well. The useful type of reflectance is what we call diffuse or specular reflectance. Okay, and diffuse or specular reflectance contains those interactions, the absorptions, the transmissions, and also the reflection. So the image on the right, so that's Chris Rolsma at one of our sites just off Peel Island, doing some coral sampling. You can see him on the bottom. This part of the photo, so this is taken from a boat looking out. So there's a diver with a tank on their back. This part of the photo is what you'd call specular, or diffuse reflectance. You can see all the colours in there. This part of the photo is specular reflectance. That is, the light hits the surface and then it just reflects away. There's no colour information whatsoever contained in the reflection. So that part of the photo, you're essentially seeing light being scattered in all different directions. All right. Whereas that's the specular one. So that's diffuse. This is what specular reflection looks like. Light goes in and then it comes back out, but it's flipped around a bit. You look at a mirror, you're looking at specular reflectance. Okay, it's just light goes in and comes back out. There's essentially no interaction of the light with what's going on there, and I can't see what's under the water surface there. So specular reflectance isn't useful. So this introduces a really key component, and it actually gets back to that diagram, is any sort of remote sensing measurement has two angular components to it. There's the angle at which you view the target from. So are you looking straight down or are you looking at an angle? And then there's also the angle that you illuminate it with light at. And so any measurement in a pixel is sensitive to both of those things. And that's a bit of a pain in the butt for a range of reasons, as I'll show you in a minute. Okay, there's more influence on specular and diffuse. Diffuse is good, specular is bad because you don't get colour information. And so when we take measurements with our handheld spectrometer, we're going to be taking these diffuse measurements. That's what we actually want to measure. Okay, those two angles of illumination and viewing I talked about before. All remote sensing measurements are bidirectional. There's an illumination angle from the sun, and then there's a viewing angle from the sensor. If you capture images basically earlier in the day or later in the day, the sun's lower in the sky. Okay, so it's at a lower angle. Right, sorry, rises in the east, sets in the west. Closer to the middle of the day, the sun's directly overhead. So there's a whole, you've got almost 180 degrees of differences in where your light source is. And then with your sensor, it depends on where your platform is, whether it's an aircraft or a satellite, and its telescope and its optics. Is it looking straight down, or is it actually looking out at an angle? And the simplest way of expressing this is that bidirectional attribute of remote sensing measurement means you can look at the same object under the same illumination conditions at different angles, and it looks very different. So that's the same forest, illuminated the same way, but just looking at different angles. So why would that be a problem with spectral signatures if you're trying to map something in an image?
Well, if it changes up the amount of light, like it will change illusions, to get gutter stuff and
Yeah, so you'll essentially, so if you were actually trying to map this particular forest, so it's a coniferous forest in North America, it wouldn't just have one unique spectral signature. It would have a range of signatures depending on what angle it was being viewed at as well. So that's one of the complicating factors of spectral signatures that we actually have to correct for. There's a lower level one. I mean, you can even, I think you see this on sports fields when they're mowed in opposing directions. In that you see one set of grass one way and then the other. That's a bidirectional reflectance effect as well.
like the spruce forest picture on the left, you could definitely, with low resolution, you think that one on the left is like a eucalyptus forest or something like that.
Yeah, so it's something which causes a lot of challenges, which we'll come back to later on. Yeah. Okay. Sorry, just on that last one, we will come back to this later on, and one of the image processing operations or corrections we go through is we can actually take satellite images and process each pixel so that it's illuminated and viewed from the same direction. And that's a really critical step if you're joining images together to make mosaics or you're doing changes over time. All right. And we'll explain how that happens a little bit later on. Okay, spectral reflectance curves or signatures. So I've mentioned these a number of times. This is just the detail. It's a graph, and on the x-axis it shows you different types of light, and on the y-axis it's how much energy is reflected or emitted. And then you plot the values for different materials. And spectral reflectance signatures, I mean, not only do they show you how much light's reflected, but they'll also show you where light's actually being absorbed, potentially emitted, and transmitted at different wavelengths as well. One of the basic assumptions of using satellite and airborne images for discriminating objects is that they have significantly different spectral reflectance signatures. If they don't, then you can't tell them apart. It's essentially like saying, from our vision point of view, two objects must have a different colour for us to see them as different if they're the same shape. So to separate objects, they need to be different. So here's just an example from this is a project that was actually done in the 2000s and has continued in a range of different forms across Australia. It's looking at an area in northern New South Wales in the map there, and it's basically north of Byron to just south of the border with Queensland in here. It's an area where there's a high density of koalas in coastal forests in that area, and we're working with a number of organisations that basically said, look, we know what are the trees or the eucalyptus species that the koalas are actually feeding on, but also spending most of their time in. If we got the spectral signatures of those, and we actually got airborne imagery with, in this case, I think it was sort of sub 20 centimetre pixels, could you map individual tree canopies and then find all the trees that correspond to the koala feed trees? So it was like, okay, let's give it a go. So we went out, and with the field spectrometers, the same type as what you'll use next week, is we went out with some of the botanists and ecologists, hired some cherry pickers and other things, and went up above the tree canopies and measured the spectral signatures of the trees that the koalas were actually eating. And we also measured a range of other trees and grasses and other features. And then went through the imagery, which was essentially that it was an airborne image flown in that strip there, went to each pixel in the image and mathematically compared the pixel spectral reflectance signature to the, what were the koala feed trees, and the yellow polygons are pixels that corresponded to the spectral signature of the koala feed trees. So you could essentially work out roughly the area. Counting them is probably a little bit harder. We did field surveys at the same time where located the trees, their height and canopy dimensions, and basically did that with the GPS. So it meant we could take the individual tree locations, which are these circles. The width of the circle is the canopy width. And we could plot what we measured in the field versus the yellow polygons, which was what was mapped from the spectral signatures, and see how well it worked, and essentially build an algorithm to do that. And that's now been applied in a range of different areas, mainly around Queensland, not so much New South Wales. This is another example. This is sort of target mapping. Okay, we're not fishing here. There's a spectrometer on the end of that boom. This is pond apple. It's a weed of national significance. So something that we've actually got from central and the southern portions of North America. It tends to get into sort of areas which are on the boundary of wet, dry areas like Melaleuca wetlands, mangroves and other things, and it goes crazy. It's not a large problem in southern Queensland. It's a quite large problem in northern Queensland. It's a weed of national significance. So the groups that were trying to control the spread of this particular weed wanted to map where it was so they could figure out where to send in field teams with herbicides to essentially kill it. So it was like, okay, same principle. Let's get the spectral reflectance signatures of the pond apple weed, and as well as the trees that it grows within. And then let's go into some satellite imagery. So this was around Innisfail, so just to the south of Cairns. It's the town of Innisfail, sugarcane fields. And then this is the Daintree River mouth down here. This is the Cow Bay area, Cape Tribulations up to the north here. And the field teams knew there was pond apple in these areas, but not how much. So same principle, go and find all the pixels and work out how similar they are to the pond apple so that you could come up with a map, and they would then send field teams in to actually apply herbicides. And that worked for a while, and they did the control. So it's just an example of how spectral signatures are used. Here's an example from more of an earth sciences perspective, and again, it's target-focused mapping. The panel on your right is the spectral reflectance signatures of a number of different minerals, okay? And if you look at the wavelength, we're not down in the blue, green and red and near infrared. We're up in shortwave infrared. So 2 to 2.4 micrometers. Sorry, there should be a micrometer symbol up here. And you can see these minerals all have quite distinctly different basically reflectance and absorption signatures. So this particular imaged area here is sort of in almost the central part of Nevada in the US. There's hardly any vegetation on it. It's where everyone tests their mineral mapping techniques. So the ground's exposed. There's a nice mixture of these minerals on the surface. So same principle, go to every pixel in the image, compare it mathematically to each of the spectral signatures, and then the signature that it had the closest match to. So, if it was very similar, let's say to kaolinite, So it matched that green signature, it was given the green colour. So that's how you went through and did the mapping. The spectral signature tells you what's there, and you can do the mapping. Taking this another level with the minerals mapping, with the weed detection, and also with the koala feed trees, is rather than just the presence or absence of a feature, is to estimate how much of it's there as well. And that can also be done from the spectral signatures. Okay, very briefly, radiation transfer theory and pathways. All of the images, the satellite images we look at, are the results of radiation transfer interactions. Everything your eyes see is a result of those things. So for you to maximise your ability to pull information out of an image, you need to understand all the different radiation transfer interactions that are going on. If it's an urban area, you need to understand how artificial features, different vegetation, bare ground, how all of those things interact with sunlight. You know, so you might have a task of, right, we want to map solar panels number of solar panels in every capital city's local government area around Australia. Go and work out how to do it and come back with a project outline. Well, that's like, okay, how big are solar panels? What are they made of? What wavelengths are going to be most sensitive to picking them up in relation to the different types of roof materials, and then use that to select a sensor and an algorithm. Or even if someone wanted to map roofing material types, which is another question. The solar panel mapping one is a real question that's been answered. If you go onto the Public Sector Management Association of Australia's website, you can look at those maps in each capital city. If you want all the details, you can actually buy it. Another problem, which is an insurance industry problem, it's actually solved as well, which is, okay, for Brisbane, which are the areas that have asbestos roofs, which have tiles, which have aluminium roofs, which have mixed composite roofs? Where are the green roofs? That's also been done as well. But figuring out how to do that, used radiation transfer interactions to figure out what sort of data to work with. Next week and then the week after, we'll start talking about different remote sensing devices. A lot of what you've seen so far is passive remote sensing. It relies on reflected sunlight or emitted thermal energy going into a sensor. There are other systems. Radar is a good example, which is radio detection and ranging. LiDAR, which is light detection and ranging. Sonar, which is a sound detection and ranging system. They're active systems. It's a little bit like a flash camera. Sends out a pulse of light and then it comes back. So active systems have their own sources of energy and work at different wavelengths as well. And we'll come back to those over the next couple of weeks. Okay, atmospheric interactions, looking at those. It's basically electromagnetic energy in the case of atmosphere going through a gas, but it's going to interact with certain other features which are in that gas, which could be liquids, whether it's like water vapor or water itself. Could actually be solids where you've got ice and or particulates and other things like that. Radiative transfer equations explain how energy passing through a medium like the atmosphere is absorbed. So, if we wanted to look at the effect of carbon dioxide, we could basically look at the wavelengths that it was absorbing. Some wavelengths of light are going to be scattered or reflected. We talked about blue wavelengths of light. It goes through a process called Rayleigh scattering, where there are certain molecules that do that. And then there's also transmission. And, we basically have equations that let us go, if you start with this much energy at the top of the atmosphere and the atmospheric composition has this much water vapor, a whole range of other parameters, here's how much light reaches the ground. So radiation transfer equations let you work out those transfers of energy as well. So yeah, the amount of sunlight at the surface or how much light's going to come back off a target. those equations are what we take and use with pixel values that are recorded in remotely sensed data sets. So we can do things like estimate, water vapour concentration over Brisbane here. If we look at water bodies, we can use a radiative transfer equation to estimate suspended sediment concentration. We could look at a radiative transfer equation to do water depth estimates based on the amount of blue and green light that we're looking at as well. So the radiative transfer equations let you turn pixel values into quantitative estimates of features. And what they do is essentially quantify each of these sorts of interactions, whether it's in the atmosphere, whether it's at the air-water interface, whether it's in the water column, or whether it's actually with the benthos or the features down here. So radiation transfer equations are essentially each of these interaction points here. And we drive them by the information that we collect in, whether it's a satellite or an aircraft. That's the information that we feed into them, and then we essentially go back through the equations to do things like estimate water vapour concentration or suspended sediment concentration, or what's the cover of seagrass underneath the water there. Okay, I'm going to switch gears now and start to talk about this week's practical, next week's practical as well. So, and the one after it too. Okay, so first of all, and I know as of just before the lecture, 73 people had signed on to the field pracs. Thanks. We'll post those lists on the Blackboard site by Thursday, so you know which day to go along to. You'll get full details of the practical sessions, what's happening in the field in the practical sessions this week. There's also an introductory video which will go up tonight about it as well. It's important in preparation for the field prac next week that you've done last week's practical and then also this week. And the field site is on campus at the end of Macquarie Street. Okay, so last week we essentially got into using the QGIS software and bringing in image data sets or image files and understanding what they actually are. So it got you used to what QGIS is and how it works. One of the questions that came up online was external students don't need to sign up. That's correct. There'll be a separate exercise for external students. So last week was here's the software and the data that you're using. What we're going to do this week is you're going to keep using your QGIS software, but you're going to go through 4 specific tasks which you'll be doing out in the field. And that's really around position measurement, so how you actually go about doing that, so you can measure your location on the ground. And it's also about how you measure environmental properties, whether it's to do with the atmosphere, vegetation, soil, or water, and link it to that position. And that's so you can integrate it with the image data. You're also going to look at the effects of different pixel sizes. So what does a 1 metre pixel look like? What does a 30 metre pixel look like? It sounds stupid, simple, maybe, and you've looked at images with different pixel sizes, but it's really important to go out on the ground and get a physical understanding of what that actually means. And we'll also be doing detailed measurements of spectral reflectance signatures in the field, but this week we'll look at using the software to do it. So last week and this week, it's all software focused, but an image focused, but getting ready for the field work. So next week, you'll go to one of the field days, you'll be in a group, you're going to collect data. And that data, you're actually going to use in week 4 in practical 1.4. And you're going to combine your field measurements with the image data sets to answer a whole set of questions. Collecting field data and combining it with image data is an essential professional skill for people working in the geospatial fields or using geospatial data. You need to be able to figure out how to go and design collection of fieldwork, collect it, process it, and integrate it all together. So you're going to create some geospatial data for integration with your other data sets. Practical 1.4 is where you put it all together, and that's week 4. And you'll go through and do that, and we'll explain what's required and what's accessible. You'll have a revision practical after that, and then you'll hand in basically a draft. So the draft assessment from 1.4 will be due on the 29th of March, and then the final will be due on the 12th of April. So that's really the progression over the next month and a half in terms of critical tasks for this class. Other than the lectures, it'll be your practicals, field data collection, and then putting it all together. External students who are listening online, you won't be doing the actual field day, but you'll actually be given data sets to work with. So rather than doing the field day, you'll have an overview video explaining field data collection, and you'll basically work through the exercises yourself. We would like people to have done this in their own locations, but I guess the legal and occupational and health safety requirements on doing it are not conducive to us doing it safely. And then after the mid-semester break, we'll come back and essentially go through Practical 2, which has 2 parts, and that is all image processing. Okay, field trips, or the field sessions, pick one of the days. We generally only want 30 people on each day because of staffing that we have. The field site's at the end of Macquarie Street on this particular playing field in here. And so if you can get down there without driving, that would be great. Please don't try and park down here if you do come here. You will see why when we're there. Toowong Rowing Club likes towing people all the time. So, yeah. Oh, and your briefing materials for the field course, it will explain when you need to be there, what you need to bring, all of those things. Generally, we like people to be there at 8:15, so we can start at 8:30. We generally won't run later than 2 o'clock, but just in case. If it's raining, it's still on. We would have to have a cyclone on top of us for it not to run. Okay, just makes it more interesting. Okay, couple of key concepts to begin with. We are going to be collecting geospatial data, all right, and geospatial data is different to data you might collect from a survey or asking people questions or a lab experiment, in that it's tied to location and time. And that means that we can look at it in a spatial context, where it is and when it actually happened. If we're looking at data that's collected over an area, particularly image data and others, there's some key things you need to know. If the terms projections, datum and coordinate don't mean anything to you, you've got a fair bit of reading to do over the next week or two to get up to speed on those things. Any geographic data has those attributes when it's actually stored. And I just want to explain what they are briefly. We'll talk about it in the prac, and we're going to talk about it in the field prac next week. A projection is essentially 2 sets of equations which lets you go from a measured location, in this case on a close to spherical surface. Whoops, the Earth's like a squash sphere. So projection lets you go from having a 3-dimensional curved object to a flat surface. So going from a 3-dimensional geometry to a 2-dimensional flat geometry. So you hear people talk about map projections. Projections are a set of formulae that goes from 3D to 2D as well. Okay, so there's different sorts of projections. Some projections preserve the shape of objects, some preserve area calculations, and some will let you preserve distance characteristics. Some projections work really well globally, some work really well over small areas as well. It's a whole field of study in itself, and it'll sort of progress. As you see, we're going to get closer and closer to geodesy and the study of the shape of the Earth and its measurement. So a projection is an attribute that geographic data will have. Datum is typically an origin point or surface, which I'll come to in a minute. Coordinate system, the coordinate systems we're typically going to work with angular systems, which are either going to be latitude and longitude. So remember, latitude is essentially degrees going from the equator as being 0 to both of the poles being 90 degrees north and 90 degrees south. Longitude is, again, an angular measurement from the centre of the Earth through to Greenwich in England. That's regarded as the 0 degree longitude. Yes, it's an arbitrary system. And basically 180 degrees east to the middle of the Pacific and 180 degrees west back to the middle of the Pacific. So latitude and longitude give you a position on the surface of the Earth. We're also going to talk about eastings and northings as well as equivalent to longitude and latitude as a different coordinate system. So key information. So the projection are the equations that transform that three-dimensional surface to a two-dimensional surface. And different projections, as I said before, distort or retain certain characteristics. I think you probably heard me comment before when we showed global maps, there's some projections that work really well around the equator, but once you get north of 40 degrees north or south, they grossly exaggerate the size of continents like the former Soviet Union, basically Canada and the US, Greenland, all of those things. So keep in mind different projections, different things. The datum is an origin point, so it can be an origin point for measuring elevation, like mean sea level. It can be the origin point for a coordinate system as well. The coordinate system defines where you are. The most simple coordinate system you've all used is a Cartesian system, which is the x-axis and the y-axis of a graph. But for position, it's either latitude in terms of sort of north or south, and then longitude, east or west, and then eastings and northings. When you take a measurement, like with the GPS on your phone or an actual position measurement system, you'll get a coordinate, and that coordinate will have been measured using a certain datum and projection. And what happens particularly with geospatial data sets is they're collected with different datum and projections, and then people go, I'm going to put them together. And as an example, you might have an aerial image of Brisbane that's collected with one datum, the current, like Australian datum that we're using, and then one from 10 years ago. You put them on top of each other. They'll sit on top of each other, but they might be out, anywhere from 50 to 200 metres. So, the locations wouldn't sit in the right spot all the time. So these are critical pieces of information to cover. We've given you some references to have a look at as well. So projections are important. Geoids and datums are important, particularly from a geographic point of view. The datum is usually mean sea level, as I said, for measuring height above. And there's ways of simplifying it. Sometimes datums are locally defined, like if you're working in Fiji, they have a datum that basically best fits where the ocean surface there and the land line up. Australia has its own datum, which it actually works with as well. If you used an Australian datum in Fiji, that's going to cause some problems with your coordinates and overlaying spatial data sets as well. Whoops. And then there's some globally applicable datums, which are based on the Earth's centre of mass, which give a good general fit. So geocentric datums, so WGS84 was one of the ones we used a lot. We switched to the geocentric datum of Australia, and we've currently got a system which continues to move and adjust year by year at the moment. We'll talk about that a little bit more next week. Coordinates, I mentioned those before. So that's latitude and longitude. Remember, latitude's north or south of the equator, longitude's east or west of meridian. Eastings and northings are the equivalent to that, but you tend to use eastings and northings for much smaller area mapping as well. We are going to talk about position measurement systems and all the different acronyms that go with it. So GNS is Global Navigation Satellite Systems. GPS came from the US Department of Defense's Global Positioning System. They're also referred to as Position Navigation and Timing Systems. Most developed countries have their own positioning and timing satellites. They're not just for geospatial operations. I'd particularly direct you to have a look at the Geoscience Australia website. It's got some useful videos about projections, datum, geoids, what are they, why they're important. They're used for like the measurements that we do in data, but they pretty much underpin all your financial transactions, our power distribution systems that send power around the country. The timing of the power distribution in terms of how they send power comes from the atomic clocks on all the positioning and navigation system satellites. So you lose those, you mess up the distribution of power around our power grid as well. So this is a whole field in itself. I'm not going to get into it, but if you do want one link to look at that link on Australia's position, navigation and timing systems. Okay, that's the end of things for this week. We'll see everybody either online for pracs tomorrow for external students, but otherwise we'll see everybody on Wednesday. If you've got questions, again, let us know via the discussion board or email as well. We'll see everyone later on. Yes, sir.